Good morning, student. I am Arnab Das. We meet again together for flowing our next topic for the transistor biasing. For transistor biasing, already we know that there are four kind of biasing configuration can be. One is the base resistor method. Second one is the collector to base bias. Third one is base bias with collector and emitter feedback. And the last one is the voltage divider bias. Last two classes already we discussed about the base resistor method, collector, and the base bias with the collector and emitter feedback. And today we discuss for the fourth one on here. Before that, we just check some important formula and also the analysis for the previous days. This is A is equal to 1 plus of beta by of 1 minus of beta DIB by of DIC. This is defined for the stability factor one on here. So if we know the value for the beta 1 and also the differentiation value for the DIB by of DIC, you can able to identify the stability factor for that particular kind of biasing. For the base resistor method, their circuit diagram as such for the first one. This is the circuit diagram where RB and the RL both are connected with the VCC. If you consider the collector to base bias, that time this RB is not connected directly with the VCC. This is connected after the RL. If you consider for the third one, that is the base bias with the collector and the emitter feedback, that time the upper portion is the same as the previous one, that is the collector to base bias. They are only added RE at the emitter side, which is connected for follow the path of grounding. Individual one, the stability factor also calculated. For the base resistor method, the stability factor is 1 plus of beta, and for the collector to base bias stability factor is 1 plus of beta by of 1 plus of beta RL by of RL plus of RB. So this is improving on here. And the third one stage there is equal to 1 plus of beta 1 plus of beta into of RL plus of RE by of RL plus of RE plus of RB. So if you check on here for the base resistor method, the improvement is occurred for the collector to base bias. Again, the another extended improvement will be occur in here also for the analysis point of view. Now we discuss for the voltage divider biasing in here. This is also specified as a self bias or also named as emitter bias. So if in here it is written as a self bias, that means this is also discussing about the voltage divider bias. If it is the emitter bias, that time also this is defined the voltage divider biasing. So you just check that what is the circuit diagram for that kind of biasing configuration. Look at there, an R2 is connect in here. This is R1 and R2. So previous one picture there only this kind of portion was present. So in here extra R2 is connected in here, and due to that modification there so much important criteria is created on there. To analyze this one, we just reflect our analysis by using the Thevenin theorem form. If we apply the Thevenin theorem, that time it will be better for the understanding and also the analysis one. Check that this portion of path, this portion of path here, this portion is connected with the base and emitter side. So we just check in here also. Look that VCC, the positive terminal, here positive terminal is connected with the R1, and then this is connected with the R2 to the grounding position, and R2 is connected with the base and the emitter side, and emitter side is the connected with the ground one. So this one will be defined for the Thevenin equivalent from R2 side, the voltage drop will be defined as a VTH, and the VTH value will become if you consider this loop, that time what happened? This is IP into of RTH plus of V of P plus of IB plus of IC of RE. Why it is coming as such? We also can able to calculate the value for the RTH also. So this is the same picture is again come on here, and to calculate the value for the RTH, that time this will be source will be used as a short circuit. So R1 and R2 will be short as a parallel form. So for the RTH calculation, parallel form value will be this is R1 R2 pi of R1 plus of R2, and for the V2, that is VTH also, this will become by uh, this particular circuit. If you apply the KVL and then you have to calculate the V2, that time V2 is equal to R2 pi of R1 plus of R2 into of VCCC. So apply the KVL for the base emitter circuit. For the base emitter circuit, this portion, this one path. So here RT is equal to multiplied with IB to get the voltage drop, this one, and then V of B voltage drop across base emitter, and for the RE side, their voltage drop will be RE into of IB plus of IC. Total summation result will become as a V of TH. Now we are applying the KVL for this one circuit, for this one circuit or path. So that time VCC will be equal to IC into of RL and VC plus of RE plus of RE into IB of IC. Okay, so that time here the RE side, that IB is omitted on that due to the reason of that the IB is very less than the value of the IC. So if you combine them, the VCC will become as a form of VCC minus of IC RL plus of RE. So now we use these two equations to get the ultimate value for the VTH also. That means if you are interested to identify the Thevenin equivalent voltage and the Thevenin equivalent resistive value, you can follow these two equations. These are the equations for the RTH. You just put this position, the value, and same way for VTH. For the VTH, this is the equation, and this value you have to put this one portion, and then you can automatically can calculate the what is the uh, equation will become on there for this one side and for this one side also. Okay, so now we are interested for the stability factor calculation. You just take the value of VTH, this kind of equation. Already we just explained this one. Their only modification is that RTH is considered as a R bit. If you think then not necessary, but in this reference, the RTH is provided as a R of B. So if you put this one, and then we have to apply this one formula for stability factor calculation. For this reason, you have to do the differentiation with respect to the IC. If you differentiate this equation with respect to the IC, that time the value will be 0 is equal to DIB DIC RB plus of RE DIB DIC plus of 1. You just do your homework as your copy also, to identify if this is coming or not. And lastly, the DIB by of DIC value will become minus of RE by of RB plus of RE. Now you just put this resultant value for DIB by of DIC in this position, and then you can got the value for the stability factor on there. So here you can able to understand that stability is improving here rather than the previous three kind of circuit diagram. So this is most effective till now for transistor biasing configuration 1. So thank you for listening this lecture.